Imagine a building so tall it reaches nearly 2 kilometers into the sky, more than twice the height of the world's tallest skyscraper today. It sounds like science fiction, but engineers have dreamed of mile-high towers for over half a century. Yet as we push higher, the challenges multiply in surprising and costly ways, and the solutions demand more than just bigger buildings. What exactly makes a mile-high skyscraper so daunting to construct? From fierce winds that threaten to tear structures apart to the limits of elevator technology, this journey to the sky is one fraught with obstacles few have fully conquered. The towering challenge. Building a mile-high skyscraper is not just about stacking more floors on top of each other. At those extraordinary heights, the fundamental issues of stability, wind forces, and material strength become overwhelmingly complex. Even the tallest buildings we have today are facing problems like sway and structural stress that demand innovative solutions. The deeper you dig into these challenges, the clearer it becomes that traditional approaches to skyscraper construction simply don't scale well. What looks like a slender monument from the ground hides a battle against physics that intensifies with every vertical meter. Beyond the obvious engineering hurdles, there is also the question of human experience and cost. The higher a building goes, the more difficult and expensive it becomes to safely move people and materials, maintain the structure, and ensure comfort at the top floors. Elevators reach mechanical limits, and the very air pressure and wind at extreme heights create conditions no one typically lives or works in. These factors add invisible but critical layers of complexity that few projects have had to fully confront yet. It's one thing to imagine a mile-high tower, and quite another to make it practical and financially viable. All these challenges point to one thing: a mile-high building will require entirely new types of structures, materials, and engineering ideas. It's not just about scaling up what has been done before, but inventing new methods that can handle the unprecedented demands. As we will see, innovations like the buttressed core began to push that limit higher, but even they have boundaries. The truth is, a mile in the sky forces us to rethink every assumption about what a skyscraper can and should be. The breakthroughs that allowed buildings like the Burj Khalifa to reach their record heights offer a glimpse into how engineering evolves in these extreme pursuits. Innovations in skyscraper design. For most of history, skyscrapers relied on a single central support system, often a concrete or steel core, to hold up the structure. This method worked well for a long time, but became less effective as buildings grew taller and wind forces grew stronger. The Burj Khalifa, standing at 828 meters, broke this pattern with a revolutionary design called the buttressed core. This system uses a tripod-like configuration, where 3 wings support each other, creating a much more stable and efficient form. It's a bit like a 3-legged stool. If one leg is slightly uneven, it still stands steady, unlike a 4-legged one that might wobble. What makes the buttressed core so remarkable is how it combines stability with material efficiency. Despite its greater height, the Burj Khalifa actually uses less steel than the older Empire State Building, thanks to its aerodynamic, wing-like shape. The design reduces wind loads and structural stress by cleverly channeling forces and resisting twisting and bending. This new species of structural system unlocked a leap forward, enabling the jump from incremental height improvements to a massive 60% increase over previous records. It's a vivid example of how architectural creativity and engineering research can rewrite what is physically possible. Wind is the hidden master controlling the fate of any skyscraper daring to reach for the clouds. Battling the wind might feel like an invisible force, but for super tall skyscrapers, it is a powerful adversary that shapes every design decision. When the wind flows around a building, it creates twisting vortices, swirling air patterns that can pull and push the structure in alternating patterns. If the building's natural sway matches the frequency of these wind vortices, it can lead to dangerous resonances, causing it to shake violently. This phenomenon is famously illustrated by the Tacoma Narrows Bridge collapse, where just the right gust set off a destructive oscillation. For mile-high towers, avoiding this kind of resonance is critical not only to structural integrity but also to the comfort of occupants. To combat the wind's relentless forces, engineers use multiple strategies aimed at confusing the airflow. Subtle changes in the building's shape, twisting it slightly or breaking it into segments, help disrupt consistent vortex patterns that might synchronize with the building's movement. Even the surface texture plays a role, with some designs incorporating openings or jump floors that allow wind to pass through, reducing pressure on the walls. These measures turn the building into a dynamic opponent that breaks the wind's rhythm, preventing it from creating harmful vibrations. Next, we'll see how the challenge stretches beyond structural elements, influencing the very experience of living and working in these sky-high giants. So like and subscribe to continue the journey. Inside the building, comfort and technology. Even after solving massive engineering challenges, mile-high skyscrapers face the less obvious but crucial issue of occupant comfort. When buildings reach extraordinary heights, they're susceptible to swaying caused by wind and structural movement. While a sway of a few centimeters might be safe structurally, it can feel unsettling or even nauseating to the people inside. To combat this, many super-tall buildings install tuned mass dampers, enormous pendulum-like weights precisely calibrated to counteract the building's motion. These devices act almost like shock absorbers, reducing vibrations and making the upper floors feel stable. Interestingly, not all tall buildings need these dampers. The Burj Khalifa, for example, relies on its buttressed core design to diffuse wind forces without requiring a tuned mass damper. However, a mile-high tower will almost certainly need one or more of these systems to maintain comfort hundreds of stories above ground. The size and positioning of dampers depend on the building's height, shape, and structural dynamics. In places like Taipei or Shanghai, the tuned mass dampers have even become architectural features, visible spheres or sophisticated electromagnetic systems that marry art and engineering. The challenge of what counts as a building adds another layer of complexity when skyscrapers reach for unprecedented heights. Defining the tallest building when chasing records, height isn't always what it seems, and measuring a building's tallest point is surprisingly complicated. Distinctions must be made between architectural height, tip height, and the highest occupied floor. For instance, antennas are excluded from official rankings because they can be changed or removed, while spires, considered architectural elements, count toward the height. That's why the Willis Tower in Chicago, despite having antennae taller than Malaysia's Petronas Towers, lost the world's tallest title since its tallest points were not permanent spires. The Chrysler Building famously exploited this by secretly assembling a spire inside during construction to leapfrog its rivals in height. The Burj Khalifa's spire adds 244 meters, making nearly a third of its total height inaccessible to visitors. In fact, 30% of some super-talls can be unoccupied spire, purely cosmetic but crucial for records and aesthetic. For a mile-high building seeking recognition, it might mean nearly half the structure is non-habitable, raising questions about practicality versus prestige. From the mysteries of structure and measurements, the story moves to the very materials and costs that ultimately decide if these astonishing towers can become reality. The limits of materials and cost. At the heart of every skyscraper lies its foundation, and for mile-high towers, this foundation isn't just deep, it must rest on the right kind of rock. Many great cities with tall buildings sit on river valleys or ports, where soil can be soft and unstable. The Petronas Towers in Malaysia hold the record for the deepest foundations, with concrete piles driven more than 100 meters underground to reach solid bedrock. This level of groundwork means roughly a quarter of the building's height is actually buried below the surface, anchoring the structure firmly against gravity and forces from above. Concrete and steel have also evolved dramatically to meet the demands of super-talls. Today's ultra-high-performance concrete, boosted by innovations like super-plasticizers, offers strength many times greater than older mixes could achieve. Pumping concrete hundreds of meters upward is no small feat. It requires careful timing, specialized high-pressure pumps, and even temperature control, like mixing in ice chips in the scorching Middle Eastern deserts to slow curing. These material advances were crucial during the construction of the Burj Khalifa, and they will need to improve even further to support mile-high projects where every cubic meter counts. Outro. Building a mile-high skyscraper is a feat that challenges every aspect of engineering, materials, comfort, and economics. While the technology to climb higher is advancing, the obstacles are enormous and require more than just dreams. If you enjoyed this deep dive into what makes mile-high towers almost impossible, don't forget to like and subscribe for more fascinating stories from the world of architecture and innovation.